Okay, now we will start with the thermodynamics law. Zero law, first law, second law, third law. There are 4 laws of thermodynamics, and why the law 0 is 0 and not 1? Because these guys, they did the other laws first, and then after we forgot this is more fundamental than the others. Then let's put it first. Let's call it 0. And then I will send you these notes actually. But the 0 law is about the thermodynamic equilibrium. You will find here. If you put an object, let's put an object A, an object B, an object C. Then the idea is if A is in equilibrium, thermodynamic equilibrium, A is in equilibrium with B, and B is in equilibrium with C, then A is in equilibrium with C. It sounds trivial, it sounds ridiculous, it sounds stupid, but it's not so stupid. And the reason is the following. For reaching the thermodynamic equilibrium, what do you need? For reaching, for example, one system is not in equilibrium. If we say, this system is in thermodynamic equilibrium, what does it mean?
So one system is in equilibrium with another, which means that the energy between them is 0. No?
The flow of energy is 0. The flow, not the end. The energy could be different from 0, but exactly. The more fundamental is they have the same temperature, because when there is no flow of energy, it means there is no thermodynamic potential. What is the thermodynamic potential? Let's revise this quickly. When we were watching electricity, the current flows from high voltage to low voltage. So the electromagnetic potential is the voltage. When a fluid is moving, the water is moving, it moves from where? From high pressure to low pressure. High pressure to low pressure. The heat is the same. The thermodynamic potential is the temperature. The heat moves from high temperature to low temperature until the two systems reach the same temperature and there is no more flow of heat. The heat doesn't flow anymore. I will give you an example. I put a glass of water here. A glass of water. Tell me a temperature. 24. K-magic. Okay, 24. K-magic degrees. And I put a piece of ice. I think you have done this in your house. If I put ice here, what is the temperature of the ice? Around 0, no? Around 0. Then what do you think will happen? There will be a flow of heat from where? From where to where? From the water to the ice, right? And then what will happen? First, the ice will change of phase, no? Phase transition, which I will explain later. So there is a latent heat, a heat which the ice absorbs and it doesn't change temperature. And then after melting, it starts to increase its temperature. The water starts to decrease the temperature until they reach an intermediate temperature. So the temperature, the final temperature will be between 24 to 0. And close to 24 or closer to 0, it depends on the amount of water, it depends on the amount of ice. If you put more ice, it's closer to 0. If you put more water, it's closer to 24. Yeah, because it depends on the amount of matter you put. So, but the conclusion is that at the end, there will be a thermodynamic equilibrium. And the thermodynamic equilibrium is reached when both objects, they reach the same temperature. That's the conclusion. Then this is the 0 law of thermodynamics. What is the most immediate application you have seen? about the zero law of thermodynamics? Tell me one application. Or practical application, like in daily life. One in daily life. Dun, 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 dun. Any idea? When you visit the doctor and you have fever, what does the doctor do? Man? What does he do? He measures the temperature. How does he measure the temperature? A thermometer. And when they put the thermometer in your mouth, let's assume that it's those thermometers, which I don't like because it's very uncomfortable to keep it. And you don't know how clean is it. In addition, how many mouths have been there? What does it happen? Your body is transmitting heat to the thermometer, and the thermometer has some mercury, some liquid, which expand when the temperature increases. And normally it's mercury. It's mercury usually. Then people know what is the coefficient of expansion of the mercury. There are ways to calculate the expansion of objects. You should know that when you hit objects, normally they expand. Up to some exceptions. The water has a strange behavior. Later I will explain that, but the water has a very weird behavior between 0 to 4 degrees. You should know that. It doesn't expand actually as it's supposed to do when you hit from 0 to 4. But in general, all the objects expand them. That's the tendency. Then, of course, your body transmits heat to the thermometer until there is an equilibrium condition. But wait a second. It shouldn't, if there is an equilibrium, it shouldn't we get the temperature of the thermometer? Why it doesn't happen like that? The thermometer is very cold initially. Imagine you put in the refrigerator the thermometer and you put in your mouth, it will reach 37 degrees. 37, 38, whatever. You have fever 40. Well, why is not the other way around? That's part of the reason, yes. That's part of the reason. The other reason, of course, we have much more degrees of freedom. No? We have the thermometer is something very small. Usually, the small object is the one which changes the most. No? I will put you an example. Go to the ocean. If you put a heat, you throw something hot to the ocean. Does the ocean become hot? No, it doesn't become hot. If I throw ice water to the ocean and it's in summer, does the ocean become frozen or the temperature decrease? No, it doesn't decrease. You know what's the reason of that? The amount, exactly. The amount of degrees of freedom. When you throw something to the ocean is a perfect sink. We call it perfect sink. Sumidero perfecto in español, in Spanish. In Portuguese, I don't know how to say. Perfeito. Sumidero perfeito debe ser, mostly. Anyway, those perfect sinks, they have infinite degrees of freedom. It's like the atmosphere. We are using cars the whole time, companies, etc., emitting gas. And do you think that the temperature of the environment, well, in the long term might be affected, but in 1 day, 2 days, in 1 month, or even years, do you think that that really affects the temperature of the environment? No, because that heat you are emitting is distributed among millions, billions of degrees of freedom. That's the difference. And of course, when you put the thermometer in the mouth, the degrees of freedom of the thermometer are much smaller than the degrees of freedom we have. It's a perturbation for us. It's a minor perturbation. It will not change our temperature. That's the immediate application of this zero law of thermodynamics. And of course, in the process of equilibrium, so we will solve these kind of problems later. You will see how to solve it. It's very easy to solve this problem. First law. Do you remember the conservation of energy? Let's increase the size of this equation. This equation here. This is the key equation. This one here. The heat, flow heat, work done by a system, change of internal energy. This is the conservation of energy. So do you remember when we studied mechanics, Newtonian mechanics, that we say, oh, there is a friction here. And then we say, the mechanical energy is not conserved. We say that, no? But that's the mechanical energy. The energy is still conserved. What happens is that we are ignoring this part, the thermodynamic part. That's the part we are ignoring completely. Okay? Now, the first law of thermodynamics is telling you the flow heat, this is heat, the total heat, plus the work in equal change. This sign is conventional. Some people, engineers, they like to put a minus here. Physicists, they like to plot a plus here. The difference is how you interpret the work. For the perspective of a physicist, when the system releases work, it's losing energy. So you take it as zero. And when receive work, it's positive. So you use this sign. But from the perspective of engineering, when the work is released from the system, is positive, so they use this minus. So it's pure conventional. But once you decide to make a convention, you have to keep it. Keep that convention forever. Keep it. Example of work. Put a piston. Let's put a piston. Well, let's find the image of a piston here because it's more beautiful when it appears in image. Piston expanding. Piston expansion. Let's put it here. This one. Do you think it will become large like this? Yeah. Look at this. This is a piston expanding. This gas here, if I input heat here. This gas will expand. So this gas will make a work over this piston. And that work, well, is calculated standard. If we take the convention of physicists with the positive sign, it will be the negative of the integral of the pressure times the volume, the volume displaced. This is integration. Of course, we will not do so many problems with the pistons and gas expandings or so. But it's important for you to know that this is like that. And the opposite, if you extract heat from this will contract. But you should know that thermodynamics started like that. Thermodynamics started as an empirical subject. And Carnot, all these guys in the past, they started to make experiments and try and error. Subsequently, statistical mechanics, which is a subject you study in master degree of physics, not in the bachelor. In the bachelor, you just see thermodynamics. And the thermodynamics for physicists is different than for engineers. Because, for example, in physics, you see second order phase transitions, which engineers don't see. But the point is that statistical mechanics could explain theoretically what these guys derived empirically in the past. Okay, specifically the concepts like entropy, which we will revise in a moment, etc. So this is an example of work in thermodynamics. The expansion of a piston. Right, excellent. So first law, energy conservation. Change of internal energy is defined different for different materials. For solids, normally, this is the mass of the object, the heat capacity, times the change of temperature. Or if the heat capacity changes with the temperature, it will be the integral of the heat capacity in the temperature from an initial temperature to a final temperature. More properly is the integration, but when the heat capacity is a constant, then the integration only falls over the temperature and it's like this. I don't know how are your mathematics, how is your integration, but I will avoid to be so mathematical in your case. It's more conceptual. I care more in concepts because actually being good in mathematics in the early stage of physics is not important. What is more important is to understand what's happening. Then after, whoever is interested can develop the mathematics and this kind of thing. What is the heat capacity? Did you listen before heat capacity? What does it measure? Temperature. Well, more or less, yeah, more or less that's the definition. It's the amount of heat a substance can receive for changing 1 degree. So that's why we use which substance it has a large heat capacity. Tell me one substance. You say, oh, this substance has a large heat capacity. The water. Hallelujah. It's the water. Why? Well, because it's like that. Well, I mean, but let's talk which application do you see of the water? Where do you see that application? The fact that the water has a large heat capacity is applied where? Well, first the oceans, of course. That's why the oceans don't change so much the temperature, of course. But what else? Yes. And no, it's not Formula One. I mean, the cars, the radiators. Radiators is the name of this. Radiador in Spanish or radiador. Quizás, perhaps it's like that in Portuguese. In Portuguese, should be like that. Well, we use water. We don't throw mercury. I mean, mercury will explode, no? Two things. First, the water doesn't expand easily. It has a low expansion coefficient. That's very important because if you put something which will expand and will explode the device, it doesn't work so well. Second, of course, it's not toxic. The third is a good refrigerator because it can absorb heat without changing the temperature so much. It has a large heat capacity. The water is considered a substance incompressible. Incompressible like the solids. It means that you can apply pressure and the volume doesn't change so much. But unless you put an astronomical amount of pressure, which will change, of course, the water can change from the state. No? Remember that the water can evaporate when you increase the temperature, can get ice, can become ice when you decrease, but also the pressure influence. I will give you an example. If I put to boil water at the level of the sea and I put to boil water in a mountain, in which case the temperature for evaporation will be lower. Are you sure? Homework. No, I mean the pressure. I will explain this because this is important. Let's put it this way. I will put a tank here. Water is here. It's open. The tank is open. The air executes a pressure against the water here. So it means when I decrease this pressure, the water escapes easier and will evaporate easier at a lower temperature. So if you put in a mountain, it will be easier to evaporate, no? The perfumes. Let's put a perfume out. Why do you smell the perfume? Why is so easy to smell? It evaporates easy. It evaporates easy. Once you open, if you let a perfume open, without closing, and you come back tomorrow, maybe half of the perfume had disappeared. It's evaporating. It's evaporating because at our atmospheric pressure is the normal temperature is the temperature of evaporation for the perfume. That's why you can smell it. The molecules of that perfume are traveling in the air, and then reach your nose. That's how it works. So, I mean, you can see physics is a series of intuitive things happening, and it has applications in daily life. Now, coming back to the heat capacity, the solids, they have heat capacity. The metals, do you think the metals have high or low heat capacity? Low, because you put some heat, you put the metal in contact with something. Well, in the kitchen, for example, the kitchen is the best example of where this happens, where the temperature of the metals changes easily. It's a good conductor, but low heat capacity. Ceramics, for example, those mug cups in Starbucks, they have high or low heat capacity. So, no, because still you can touch, and it's not that you can put your naked hand on. Well, of course, they can resist probably more temperature than the metals, no? The ceramics. Remember, the ceramics as the materials they use for the transbordador, no? The spaceships, for resisting the heat of the atmosphere during the re-entry. This formula is valid not only for solids, also for liquids. Solids and liquids. You can use this. If the heat capacity doesn't change so much, you can use an average value here and use this simple formula. If you know the way of the heat capacity change with the temperature, then you use the integral, the integration. Excellent. Let's delete this part. So the heat capacity of gases, also with similar formulas, but there is an issue. While for incompressible substance, there is no difference between the processes at constant pressure or constant volume. For the gases, it matters. So the gases, you define two heat capacities. One heat capacity at constant pressure and one heat capacity at constant volume. You will listen, oh, the heat capacity at constant pressure for the gas, for this gas, neon or whatever, argon or whatever. The heat capacity at constant volume, but for the solids, these two quantities are the same. And for the liquids, approximately they are the same. How do they measure these two quantities, and which one is larger? Which one do you think is larger, the heat capacity at constant pressure or the heat capacity at constant volume? And you can know that intuitively. You don't need mathematics for that. You can guess even by logic arguments, physical logic arguments. You don't have to memorize it, only you have to analyze. Because this is the way how I studied when I was younger. I mean, it's not memorizing, it's you try to find the way to understand these things, and after you say, hey, you don't have to memorize after all. This is a natural way to learn. Then can you tell me, think in your desk for a moment, which one is larger, constant pressure or constant volume? Remember, what is the heat capacity? Remember, heat capacity is the amount of heat you inject in a substance for it to change in 1 degree. And this is per unit of mass. No? This is the specific heat capacity. It's per unit of mass. So it's independent of the amount of matter. Because after you multiply by the amount of matter matters, of course. The amount of mass matters, but the heat capacities are defined independent of the amount of mass. I don't like when this happens. It's like a sabotage, but now it's okay. It's back. And it went to the wrong. Okay, here we are. Anyway, so which one is larger? Let's do an exercise. I will put this. I will paint something on the board. Here in this part here, in this part white, with a different color. I will put a piston, a tank here, a cylinder, and you will understand how which heat capacity is larger.
Temperature and pressure directly proportional to each other at constant volume.
Well, that part, you will guess it now. You will see. But yeah, that's more or less what is happening. The pressure plays some role also. Of course, the pressure plays some role. But look at this. Look at this. You have this. These markers are really bad. I don't know why I always match with the bad markers. But let me see if this one works. This is a cylinder. Let's put a piston here. And this guy is free to move. Free to move. When I input heat to this system, actually in this formula, this is not the flow heat. I think I said flow heat a few times. No, it's the total heat. Total heat. Total heat, because in thermodynamics, something very important you should know is that thermodynamics study the equilibrium conditions. Here we don't care the process. We stay one state of equilibrium, second state of equilibrium, and we evaluate the changes between one state and the other. We don't care what happened in between. We don't care. We don't care. Well, we care, but we care in these two quantities because these quantities depend on the path, but thermodynamics itself evaluate conditions of equilibrium. And later I will explain you what's the difference between these three guys subsequently. It's different to heat transfer. Heat transfer is another subject, and that heat transfer really studies the process of flow heat, which maybe we can see a little bit of heat transfer later because there is an analogy with circuits or so. Well, anyway, come back. You want to say something? Sorry, because I interrupted you.
No, I said everything. I think it was temperature and pressure having a directly proportional relationship with each other.
Okay, let's compare these two things. This is a case. I enter heat here. The piston is free to move. Evidently, this process is not a constant volume. This process will be a constant pressure, and there is a gas here, which expands freely here. Now let's go to the other case. The same tank, but now this is a wall, fixed, and I enter heat here. This is a process, a constant volume. The volume doesn't change. So I will tell you something and you will guess immediately which one, in which case the heat capacity is larger. I enter heat to this. Then the gas tries to expand. I cannot expand. Oh my God, what's happening? All that energy goes to increase of temperature, to the motion of the degrees of freedom, because the temperature is the kinetic energy of the degrees of freedom of the gas. The molecules of the air start to do many things, collide each other. Yeah. Sorry, I'm not crazy. It's just this guy's crazy now. And in this case, in the case of the free constant pressure, part of the energy goes to the expansion, is wasted in the expansion. And part of the energy goes to increase the temperature. So naturally, the temperature will increase more here, giving the same amount of heat. Then now you can guess which heat capacity is larger, constant pressure or constant volume? Constant pressure. So the heat capacity at constant pressure is larger, and you will always see in the books they say Cp is larger than Cv. Always. Then you don't have to memorize that. You have to memorize, no. But you know, when I was in bachelor degree, the professors didn't explain this way. Because some people might believe, no, this guy explained like this because his professor explained like that. No. The guy who was teaching us didn't explain like that. It's because I read from the textbook and Not even the textbook explain like that. It's like after thinking, you start to guess, it should be like this, it should be like that. But sometimes not even the textbook explain these things in the way or just plain while explaining now. So heat capacity, constant pressure is larger than heat capacity at constant volume because it's more difficult to increase the temperature at constant pressure than increase the temperature at constant volume. That's the reason. Excellent. So for the gases, of course, the internal energy is defined at constant volume. Internal energy, this, the change of internal energy in a gas is mass of the gas, heat capacity at constant volume, change of temperature, this is an average, but more precisely is the integral of from initial temperature to a final temperature at constant volume. And then what happens with the constant pressure? That's when we use the concept enthalpy. Enthalpy is another thermodynamic quantity, which I will explain subsequently, but when you use enthalpy, then in summarizing this part, of course, there is conservation of energy here. Heat, normally, we will take this convention with positive, not with negative. Later, I will share with you. But we will take this positive because for us, the work going out from the system will be negative. And the work entering the system will be positive. If I push a piston, I am inputting energy to the system. So I will take that as positive. If the piston is releasing work, it's losing energy, so I will take this as negative. So I like this convention. It's more logical from the perspective of physics. So the sum of these contributions, heat and work, is equal to the change of internal energy. It comes out that in the expansion of gas, this is minus integral P dV, or in average is minus P, change of volume. And if you move this to the left-hand side, this will become delta U plus P delta V, and this is what we call change of enthalpy. Enthalpy is another thermodynamic property, and this one is the one which is the integral of the heat capacity at constant pressure, the T multiplied by the mass, temperature initial, final. So the enthalpy, sometimes people for economy, you will find the thermodynamic tables, and when they evaluate some thermodynamic properties or processes, they use enthalpy instead of internal energy, because sometimes it's easier to do it in that way. Excellent. So, because in the past, many people are really evaluated what is the change of enthalpy for certain liquids, for certain materials, for certain gases, for certain change of internal energy. Many people did those studies in the past. Then you only have to go to the thermodynamic tables and say, is this, and blah, blah. This session, I will not see phase diagrams. I think phase diagrams we will explore next session. But it's very important because the change of phases is one of the most important applications of thermodynamics, actually. Okay, I think this is all for the first law. Some final comment about the first law of thermodynamics is that this differential, if I write this in differential, this will be the U. This is an exact differential. But for the heat, I use this. And for the work, I use this. And this is in exact differentials. Why in this way? Because the changes in internal energy, they don't depend on the process, of the trajectory of the process. I will give you an example. If I have a piston here, let's assume I have a piston with some liquid, particular liquid or gas, let's put a gas here. And I input some heat, there is a work, whatever, there is a change of internal energy. And now I do so the energy enters here, and these pistons will expand, whatever, but there will be a change of internal energy. Now I have a completely different process, a tank, isolated, whatever, and I input. And with the same change of these two processes are completely different, and they can have the same change of internal energy. So the left-hand side of this equation will be identical for both processes, but the right-hand side will be completely different. So it means the right-hand side cares how the process is done, while the left-hand side doesn't care how the process is done. That's why people use exact differentials for the left-hand side and inexact differentials on the right-hand side. In a thermodynamic diagram, for example, a thermodynamic diagram putting pressure and volume. Normally, you will find PV diagrams in thermodynamic cycles, for example, in engines, in motors, and so on. And you go from one point here to a second point. This is an expansion because it comes from a small volume to a second volume. And I will put this line here. So this point has an internal energy 1. This point has an internal energy 2. Okay? The change of the internal energy doesn't care this process in between. But the work, this work depends on how I made the process, because if the process is not like this, but instead it's like this, or if it's like this, the amount of work and the amount of heat will be different. So in other words, the heat and the work depends on the trajectories that the process takes, but the change of internal energy doesn't depend on the trajectory the processes take. And believe me this, because I was the best of the best of the best student in thermodynamics in my bachelor degree, so I understand these concepts very well. I explain to everybody in the class. I guarantee you. Universidad del Norte, I think that I will share this video with them, and they can guarantee Ivan was the best in thermodynamics. Thermodynamics 1, thermodynamics 2. So trust in what I say here. Then let's delete this part. Of course, it will be time for break, but before the break, I will mention something. We will come to the second law. Second law touches the change of entropy. Do you remember we mentioned entropy here a few times, no? What is the entropy? It's related to the energy you cannot use, irreversibilities, irreversible processes, all these kind of things. For example, I throw this marker to the floor. Technically, when the marker is falling, it's doing this. When the marker is falling, technically that energy, I can use it during that process. But when the marker falls, that energy is dissipated on the floor in many, many degrees of freedom on the floor. The molecules of the floor or the material of the floor start to vibrate, to dance, to make some harmonics. And we cannot use it. At least we don't know how to do it right now, no? But technically, it's true that we have a lot, infinite amount of energy surrounding us, and we don't know how to use it. It would be great if someday we could use these things, no? But anyway, for the moment, let's take a break. It's 4:30. We will take 25 minutes or so break, then I will stop this recording.